Hi all. Today we are discussing the problems on calculation of losses of pre-stress. So in first problem we'll start a pre-tensioned concrete beam of rectangular cross section 150 mm wide and 300 mm deep is pre-stressed by 8 high tensile wires of 7 mm diameter located at 100 mm from the soffit of the beam. If the wires are tensioned to a stress of 1100 Newton per mm square, calculate the percentage loss of stress due to elastic deformation, assuming the modulus of elasticity of concrete and steel as 31.5 kN per mm square and 210 kN per mm square respectively. So this is the question given. We have cross section 150 mm wide and 300 mm deep. You can observe in the question it is given the location of wires is 100 mm from the soffit of the beam. That 100 mm is not eccentricity, it is a distance from bottom of the beam. With respect to centroid of the cross section, we need to find out what is the eccentricity. So overall depth is 300. So centroid will be 300 by 2 150. So eccentricity is 150 minus distance from bottom to cables or tendons, that is 100 mm. We will get eccentricity of 50 mm. And area, it is 0.15 by 0.3. Moment of inertia we have calculated. And in question, the pre-stressing force is not given directly. Here the number of wires and the diameter of the wires is given, and a stress per mm square area is given. So we need to find out the total area of the tendons or total area of the wires, and we need to multiply it with what is the stress per mm square. So that we have calculated here. Pre-stressing force is stress in steel into area of steel, that we got 338.663 kilonewton or 10 power 3 newtons. So this is the formula to calculate stress in concrete at the level of steel. Remember this formula: P by A plus M by I into Y. Okay, so here P is directly given, area we have calculated, M is moment with respect to pre-stressing force about centroid of this section, that is eccentricity. PE by I, M is equal to P into E, and into Y. Here in formula we have Y, that we have considered here E. That Y indicates it is not eccentricity, it is the distance of tendon to the centroid of this section. Remember this, Y is the distance of centroid to the tendons. So that is, sometimes it may be E, but in different cases it may changes. So in next problem we can understand that clearly. So for this problem, Y is nothing but eccentricity only. So here we have calculated sigma C. So loss due to elastic shortening, we have formula modular ratio into stress in concrete at the level of steel. So we have modular ratio elastic modulus of steel by elastic modulus of concrete into stress in concrete at the level of steel. I have calculated this. So here we have total pre-stressing force, and this is the loss. See here, percentage loss, it is per mm square, and we have calculated here loss of pre-stress, it is not force. So we can directly calculate here initial stress, loss of stress upon initial stress into 100. You will get what is the loss of percentage loss of pre-stress. That's it. Here remember the formula, sigma C equals P by A plus M by I into Y. You should remember this. P we have, it may be directly given or it may be given in terms of area of steel and initial pre-stress. M, it is the moment of pre-stressing force with respect to centroid, that is P into E by I, and Y, it is the distance of tendons to the centroid of the section. So let's go to next problem. A rectangular concrete beam 300 mm deep and 200 mm wide is pre-stressed by means of 15 number of 5 mm diameter wires located 65 mm from the bottom of the beam and 3 5 mm diameter wires located 25 mm from the top of the beam. If wires are initially tensioned to a stress of 840 Newton per mm square, calculate the percentage loss of pre-stress in steel immediately after transfer, allowing for the loss of stress due to elastic deformation of concrete only. Take ES 210 kilonewton per mm square and EC 31.5 kilonewton per mm square. So here we are having cross section of the beam, and read the question carefully. He is given 15 number of 5 mm diameters wires located at 65 mm from the bottom of the beam. So at bottom we have 15 number of wires and 3 number of 5 mm diameter wires located at 25 mm from the top of the beam. So you can see at top we have 3 wires and at bottom we have 15 wires. So in this case, see, we have 2 layer of wires, one at the top and one at the bottom. So we need to find out the unique centroid or single centroid for both tendons to get eccentricity. So that we have calculated, we need to calculate area, it is known. In moment of inertia we can calculate pre-stressing force. Total number of wires we need to consider 15 plus 3, total 18 number of wires into initial stress into area of steel, we will get 296.8 kilonewton. So here distance of centroid of steel from the soffit of the beam, that's what first we need to calculate distance of centroid from the soffit is nothing but bottom of the beam, and that value we obtain 100 mm. Y is 100 mm. This Y is not in the formula. This is centroidal distance of the 15 plus 3, 18 cables from the bottom of the beam. So the total depth of the beam is 300 mm and centroid will be 150. So 150 minus 100, we will get 50 mm as the eccentricity. Yes, now see here y1 and y2. Here y1 is 150 minus 25. As I said in formula, in the formula P by A plus M by I into Y, this Y value for top layer we have 3 cables. So those 3 cables are located 125 mm away or above the centroid of the section, and Y2 similarly 15 number of cables are located below the centroid of the section of about 85 mm. So those values we need to substitute. So first we have considered in bottom steel, that is 15 number of wires, P by A into PE by E into Y2, that is distance of 15 number of wires and centroid of the section, overall section. There we have got sigma C value. Calculate loss of stress. Modular ratio is elastic modulus of steel and concrete are given, and you consider sigma C value. You will get loss. So for that, what is the percentage loss? Same way, loss of stress in top steel, that is 3 number of cables we have. For that, the centroidal distance, the distance of 3 cables from the centroid of the section is 125 mm, that is 0.125 here. You should remember this clearly, how to consider Y value. Okay, so this is sigma C. Again, the procedure is same. We have modular ratio into sigma C, percentage loss. Next, we'll move on to next problem. A post-tensioned concrete beam 100 mm wide and 300 mm deep is stressed by 3 cables of cross-sectional area 50 mm square with an initial stress of 1200 Newton per mm square. All the 3 cables are straight and located 100 mm from the soffit of the beam. If the modular ratio is 6, calculate the loss of stress. The 3 cables due to elastic deformation of concrete only. For the following cases: first case, simultaneously tensioning and anchoring of all the 3 cables, successively tensioning of the 3 cables one at a time. And remember, see, this problem is very important one, you should understand clearly. Here in question it is given post tensioned concrete beam. Okay, it is post tensioned member, and we have 3 cables of cross section area 50 mm square. So if we draw the cross section, it is 100 mm wide by 300 mm deep. So centroid will be at the 150 mm, and the cables are located at where it is given 100 mm from the soffit of the beam. So the eccentricity will be 50. Area we have, moment of inertia we have, load, pre-stressing force, initial stress is given, and area of steel is given. So it is 60 kilonewton. Now since we have only single layer, no need to worry, we can consider Y as eccentricity. We have calculated sigma C value 2.67 Newton per mm square. Yes, now the next thing is very important one. Loss of pre-stress due to elastic shortening of concrete when all 3 cables are tensioned simultaneously. So in previous class I told, if the number of cables are tensioned simultaneously in case of post tensioned beam, then the loss due to elastic shortening is 0. If all 3 cables are tensioned simultaneously, that is at a time we are applying the tensile force for all 3 cables, so in that case there is no loss of pre-stress, and the loss will be 0. See here, no loss of pre-stress due to elastic shortening of concrete when all the 3 cables are tensioned simultaneously. This is the answer for first case. Next, second case, loss of pre-stress due to elastic shortening of concrete when the 3 cables are tensioned successively, that is one after the other. So in that case, first we will apply the tension for one cable. Okay, so when you applied the tension force or tensile force for first cable, you are just stretching the cable and remaining 2 cables are at rest. We have not touched it. We are not touching remaining 2 cables. We have applying the force for only one cable. So in that case, still we are applying the tensile stress and we have not yet released the first cable, so there is no loss because remaining two we have not at all touched. So loss due to pre-stress in first cable is also 0 as we are applying the tensile stress, and second and third cable also 0 since we have not touched. Next, when the second cable is tensioned, yes, here the important thing you need to remember, when you have stretched the second cable, first you need to fix up the first cable which we have applied the tensile stress, that you need to fix it first, then you come to second cable. So while fixing there will be certain amount of stress will be lost. So for that we have formula modular ratio into stress, we have this, and you are applying the tensile stress for second cable, you are stretching it and you have not yet touched the third cable, so there is no loss in these two cables, that is second and third cable. There is a loss in first cable since you have fixed it, and there is no loss in second cable since you are pulling it, and third cables you have not yet touched. Then when you come to third cable, you need to fix up the second one also. So while fixing the second cable, again there will be certain amount of stress is going to loss in first cable. So in first cable you need to find out the loss of stress twice. The loss of stress will occur twice in first cable and once in second cable. Okay, so same formula, the modular ratio into stress in concrete at the level of steel, that is sigma c. For both cables you need to find out, for first cable as well as second cable. Then you are pulling the third cable, so in that case it is 0. So total loss in first cable, some amount of loss while stretching the second cable and some amount while stretching the third cable. So 2 times there is a loss of stress, so we have 2 times we have considered here. And for second cable there is a loss of stress only while you are stretching the third cable, so it is once and there is no loss. So if you add these two you will get total loss. And next, a post tension concrete beam, this is the next problem. Post tension concrete beam 100 mm wide, 300 mm deep, spanning of 10 meter, is stressed by successive tensioning and anchoring of 3 cables 1, 2, 3 respectively. The cross section of each cable is 200 mm square. Each cable it is given, be careful. And the initial stress in the cable is 1200 Newton per mm square. Alpha E, it is modular ratio, is 6. The first cable is parabolic with an eccentricity of 50 mm below the centroidal axis at the center of the span and 50 mm above the centroidal axis at the support sections. The second cable is parabolic with 0 eccentricity at the supports and eccentricity of 50 mm at the center of the span. The third cable is straight with an uniform eccentricity of 50 mm below the centroidal axis. Estimate the percentage loss of stress in each cable if they are successively tensioned and anchored. So you can observe the figure carefully and understand the question. So this top one is first, middle one is second, and straight is third cable. Okay, so if you first will let us consider first cable. So here it is given the profile of first cable. The first cable is parabolic with an eccentricity of 50 mm below the centroidal axis at the center of the span. That is, if you consider mid span, there we have eccentricity of 50 mm below the centroidal axis and 50 mm above the centroidal axis at the support sections. So if you consider support, there we have 50 mm above the centroidal axis. So we have eccentricity at the support of 50 mm and at the mid span of 50 mm for first cable. Then come to second cable. The second cable is parabolic with 0 eccentricity at supports and eccentricity of 50 mm at the center of the span. So second cable we have 0 eccentricity, that is it is coincide with centroidal axis, and at mid span it is 50 mm of eccentricity, and third cable is straight with a uniform eccentricity of 50 mm below the centroidal axis. Then third cable is straight one. The span is 100 mm. We have cross section of 100 by 300. So in this problem you need to remember one more formula while calculating the loss of pre-stress for parabolic cables. We need to take the average stress while calculating the sigma c value, that is stress in concrete at the level of steel. We need to consider the average stress in concrete. So average of what? Stress in concrete at support and stress in concrete at mid span. So for that we have formula, you need to remember this. We need to calculate stress in support and stress at mid span, and by considering those two values we can calculate sigma c average by using this formula. Sigma c at support plus 2/3 of sigma c at mid span minus sigma c at supports. This is the formula, you have to remember this. How to calculate the stresses we will see later. Yes, now so as in case of previous problem, when you tension first tendon you are applying the tensile stress and you have not at all touched second and third cable, so there is no loss in any of the cable. So when first cable is tensioned there is no loss. Then come to second cable. When you have tensioned the second cable there will be some amount of loss in first cable, but there is no loss in second and third cable as you are tensioning the second cable and third cable is not at touch. So first we need to find out what is the loss of pre-stress in first cable, which we are fixing it. So same formula we can use. See, bending moment due to pre-stressing force in the tension tendon 2 at the support P into E, but E is 0 at the support for second tendon, and Y is the distance of centroid of the tendon 1 at the support. This is very important, you should be very careful here. Bending moment P into E, what you are going to consider. So P we have calculated, area we have, moment of inertia we have. Here we are tensioning the second cable. So bending moment of pre-stressing force for second cable we need to consider, and Y value in the formula. See here, M is P into E. So for that E eccentricity we need to consider for second cable, as we are tensioning the second cable, and Y value we are calculating the loss of pre-stress in first cable. So at support for first cable we have eccentricity of 50 mm above the centroidal axis, that we need to consider here, 0.05 meters. It is very important. So as the eccentricity is 0 at the support for second cable, so there is no matter of P into E by I into Y, so we neglect it. We have only P by A. We have stress in concrete at support is 8 mm. Okay, then compressive stress in concrete at level of steel at mid span. So here we have eccentricity of 50 mm for both second tendon as well as first tendon. So here P into E is eccentricity of the second tendon, it is 50, and 50 mm for the first tendon, that is Y value from centroidal axis we have first tendon at 50 mm distance. So those values we have to consider here. So for that we have sigma c at mid span, and by using formula we have to calculate average stress. This is average stress is 9.77 Newton per mm square. Then we can calculate the loss of stress due to elastic shortening by using formula alpha E into sigma C. Modular ratio into stress. So we have loss of 58.62 Newton per mm square in first cable when you have tensioned the second cable. Then when the third tendon is tensioned, remember previous problem, when you tension third tendon, you need to find out the loss in both second as well as first, but there is no loss in third tendon. So there is no loss of stress in third tendon, and there is a loss of stress in first and second tendon. So first let us consider first tendon. So compressive stress, again you need to calculate sigma C at support, sigma C at midspan, and sigma C average. So sigma C at support, for the formula you are tensioning third tendon, it means third one is straight tendon with uniform eccentricity of 50 mm. So eccentricity at support for third tendon is 50 mm, and distance of centroid of the section to tendon at the support is 50 mm above the centroidal axis. So that is both E and Y we have to consider 0.05 meters, that is 50 mm. Sorry. And we can calculate the at support section. Same way, when you come to midspan section, we have eccentricity at both 5 mm, sorry, 50 mm. So substitute the value, you can find out it. And one thing you have to remember, at support section, the first tendon is above the centroidal axis, so we have to consider minus. Here it is plus because both are below the centroidal axis. So sigma C average, then modular ratio into sigma C. Then loss of stress in second tendon, same way, again it is also parabolic tendon, but here you should remember the eccentricity at support for third tendon is 50 mm, but the eccentricity for second cable at support is 0. It is coinciding with centroidal axis. So E will be 50 mm and Y will be 0 for second tendon. Substitute the values, we will get sigma C at support. At midspan both will be having same eccentricity, so you have sigma C at midspan. Calculate the average stress, then loss of stress, then you need to add all the things, loss in first tendon, loss in second tendon, and all the tendons you need to find out. Let's move on to the next problem. A simply supported concrete beam of a uniform section is post tensioned by means of two cables, both of which have an eccentricity of 100 mm below the centroid at midspan. The first cable is parabolic and is anchored at an eccentricity of 100 mm above the centroid at each end. The second cable is straight and parallel to the line joining the supports. If the cross-section area of each cable is 100 mm square, the concrete beam has cross-sectional area of 2 into 10 power 4 mm square and radius of gyration of 120 mm. Calculate the loss of stress due to elastic shortening of concrete when second tendon is tensioned to a stress of 1200 Newton per mm square. Take the modular ratio as 6 and neglect friction. So remember, see here first cable is parabolic, anchored at an eccentricity of 100 mm above the centroid, and both cables have an eccentricity of 100 mm below the centroid axis. So that means first cable is having 100 mm eccentricity at support as well as at support above the centroid and at midspan below the centroid, and second cable is straight with an uniform eccentricity of 100 mm. This is the case. Here area is directly given and radius of gyration is given. Where we need to use, we will see later. So area is given. See, to calculate I value, radius of gyration is K is equal to root of I by A. So we can calculate moment of inertia directly. So P, stress in steel into area of steel. Area of steel is given 100 mm square. So we'll get 120 kilonewton. So this is the profile of the tendon, 100 mm at support and 100 mm at the midspan. So when first tendon is tensioned, there is no loss in any of the tendon. When you tension second tendon, here you should be very careful. For moment, bending moment due to pre-stress, tension in tendon P into E value will be 100 mm for straight tendon and 100 Y will be 100 for parabolic tendon, but at support we have first tendon above the centroidal axis, so P by A minus M by I into Y. We will get sigma C at support. At midspan, both are below the centroidal axis with an eccentricity of 100 mm. So we have sigma C at midspan. Calculate average stress and loss of pre-stress. So this is about basic problems in the loss of pre-stress. So in next class we will continue with further more problems. Thank you.